Yeah, good afternoon. Sorry for the context switch. Since I'm a roboticist, I'm not a planner. So, and being a roboticist inside ICAPS but outside PlanRob may still be the rare case. Hopefully it's going to be a commonplace in future. But anyways, this is one reason why this is a context switch. Another reason is that I'm going to talk mainly about service robots. So service robots are those robots which are supposed to help elderly people do pick and place tasks or do surveillance or something like that. And our main aim in this service robotics domain is actually to make them more reliable. More reliable especially means that we want to enable them to deal with unexpected situations. Of course, this is then some connection to the planning domain. What I'm going to present is actually the work of my PhD candidate, Anastassia Kuestenmacher. She excuses herself for not being here for family reasons. A former master student of mine, Naveed Akhtar, and a colleague of mine, Gerhard Lakemeyer, who is with the Technical University of Aachen. My name is Plöger, and the main aim of this talk is actually not that many formulas, not that many proofs, but to wetten your mouth, actually to have a look at this article. Yes, this is in the journal track, and so this has been published in December 2013 in this Journal of Intelligent Robotic Systems. So please have a look. You can lean back since this is very easy going. Yeah? Okay, so this is actually, let's say, the motivation of what we are doing. Let's assume that this little humanoid robot now is trying to place a die on a table. Now you, as a human, looking at this picture, immediately know what's going to happen, since you will see or predict that this die is obviously falling down from this table, since the initial pose of this die on top of this table is not really, really nice. And as such, some effect, which is going to be fulfilled by this action being executed, will most likely fail. Okay, so bad luck, but unfortunately I think it is needed that we compensate for that. I would like to stress two notes, and here one note is actually that the prerequisite which we have is that all internal components of this robot are supposedly working perfectly fine. As such, classical theories of failure, detection, analysis, isolation, and so on will not be applicable, since they do presume that the fault is actually a part of the system. Of course, looking at this thing here, it's already a very difficult task to answer the question, what is the system here? Since we have one system here, but is the environment already a system? Or is the interaction of the robot to this die a system? And actually, this is one of our real big problems. We lack sufficiently good models for our environment. So this makes our task to really enhance the functionality of the robot very complicated. So these kind of situations actually cannot be fully accounted for during the design time. So there's no chance to address all of them. They occur often, very often, actually, most of the time, while the robot is interacting with its environment. And last but not least, we still have some prerequisite on detectability. So they are detectable in the sense of course, some plan monitor, some action monitor is able to say some of these sub-goals have not been reached, since the properties of objects which we can quantify has not been accomplished. So the values are different, and as such we can say, yeah, some bad thing has happened. Because of this technical issue of not being able to call it a fault, since a fault is a part of the system, we strive for a new name, and so what we are going to call it now in this talk is actually unexpected situations. Okay, so the unfortunate thing with unexpected situations in robotics is that they are ubiquitous. Yeah? So it's not just one example, but look at all these other examples. So here, for example, a small omni-wheeled U-bot is trying to deliver a cup on a chair, and because its perception devices are not recognizing the legs of the chair, it's actually crashing to the chair. So this could be called an imprecision of perception devices. Or look at our main service robot, Jenny. She's trying to go from A to B, and she's impeded by a whole bunch of kids right in front of her. So this is an external disturbance by which she is hindered to actually accomplish this goal from going from A to B. Last but not least, another common category of unexpected situations is actually caused in previous inaccuracies. So here, for example, Jenny is trying to actually deliver a Pringles can on a table, but since she picked it up in a slightly slanted, oblique way, so also this action is going to be likely to, or deemed to failure, let's say. Okay. Now, as you have these many different variants or categories, it's very likely that not a single approach is able to deal with all these situations. So you can deal with some kind of these situations like using belief management. You can do replanning, of course. You can use estimation methods like HMMs. But for now, and here and in our article, I want to concentrate actually on two aspects, namely one which I call, or which we call actually qualitative reasoning approach, QR approach, and the other one called simulation-based approach. This first one is actually giving reasons why things go wrong, and the second one is trying to remedy this. So this is actually something like learning. And this learning is based on the assumption that we are in a plan-based system. And as we are in a plan-based system, this approach is actually trying to remedy this inadequate description of the planning operator and get a better planning operator instead. It's actually in the line of Manuela Veloso, Prodigy 90s. Yeah, so it's actually picking up on that. She used different procedures at that time, though. Yeah, so we are a little bit different from that. Okay, so let's have a look at qualitative reasoning. Now, humans actually operate in the same environment as the service robots, and humans are very strong in this removal of faults, yeah? So they can actually do it. And now, how can they do it? Well, they do it because they are able to reason in terms of not mathematics or not quantitative data, but they do it qualitatively. And this thing was picked up by a smart guy, an AI guy, Pat Hayes, at the mid of the 80s. Once again, second naive manifesto, 1995. And he suggested to formalize everyday knowledge of physical world used by naive reasoners to a declarative symbolic theory. Now, this program didn't really catch on because it was so much oriented towards a complete knowledge representation. Instead, end of the 90s, Ernest Davis came up with an alternative to that, which is called microworlds, which he defined as abstractions of small parts of physical interaction sufficient to support some interesting collection of interferences. And this is actually the definition which we strive for and which we are going to use in our work. Okay, if we combine qualitative reasoning and this unexpected situation, what's the outcome? So we actually programmed something like an hypothesis generator. What is this hypothesis generator generating? For any situation like that, it uses actually quantitative state information about those objects being involved in this activity. So here, for example, you see that the state of the die can here actually be described by the place of the die is on the table, the translation, which is actually bad name for the motion state. The motion state is moving, and of course here the stability of this die on the table is actually unstable. The good news is that this here, when you know how this is how this was constructed, actually can be literally translated one-to-one, word by word, into commonplace plain English. So these things can be read as there existed some interval of time after the release of the die, of course, where the die was on the table, place table. Its center of gravity was not fixed at that point, translation moving, and the projection of the center of gravity straight downwards actually left the top of the table for at least one instant of the time of that interval. Okay, so this is the good news. Now, how did we accomplish this hypothesis generator coming up with this hypothesis for this fault happening? We constructed a logical framework based on prologue clauses and facts and constants. So here is, for example, one example for this instability issue, which I mentioned on the slide before. So you see here that this can be modeled by, this situation can be modeled by the object has to be on the other object. The coordinates of this first object using its center of gravity and then making a line from the center of gravity pointing downwards will never hit here the tabletop, and as such it is unstable and will fall down. Okay, note in this definition, though, that the properties may be valid over some time intervals, so we don't want to go for time logics and so on, so keep this out because it's a very deep area for now. And also, some of our definitions which we give here in prologue clauses have some bias towards certain fault categories, so right now we actually favor localization faults. If you want to add more different kind of faults to our current theory, you have to use additional microworlds. Okay, so far to these QR-based naive physics concepts for finding causes of unsuccessful executions. So how about actually remedying them? So how can the robot learn from its own faults? And this is what we call simulation-based approach. It's based on the assumption that we have a plan and plan operators. So here are two samples of plan operators. So we have a traditional operator name, precondition effects. And what we are striving for is a modified operator. And this modified operator is actually distinctive from this one by this preconditions, which has this clause allowed. Inside this allowed clause, actually, this is going on. So we use a simulator as an oracle. We need some positive seed. This positive seed can be subjected to a logical clause being composed from 1 to 5 different, let's say, atomic clauses. These atomic clauses are based on RCC8 relationships, for example. They can be used to actually label this successful experiment. Knowing what a successful experiment is, we can do massive parallelly simulation on open state variables, like here rho pitch yaw. And after this massive parallelization, actually we find bounds of these open intervals to be, let's say, emulgated or to be mapped to this allowed statement. What's the outcome of the simulation-based approach? So you can see here that we have, let's say, this is what I explained on the other slide, but here it is possible from dropping, let's say, an initial seeding situation, having a single object on a table is able to also find good drop places for, let's say, an inhabited table, or we are even able to learn, for example, to throw a ball into a basket. Since we vary speeds and rotational speeds, this is possible. Yeah, and actually, the only open problem is generalization of this, since this is happening in the simulator, so we are bound to object and instantiations. So what we want, of course, we want to work on object classes and instantiation thereof. So summary is, I gave you a glimpse on what is naive physics good for in the reasoning about unexpected situations. I also explained some simulation-based approach to you, how we learn and fix a plan operator using heavily simulation. And the open issue right now in current research area is actually the combination of symbolic and numeric approaches, which was mentioned in the Plan ROP workshop also yesterday. I think this is one of the very intriguing, actually this interplay between numeric and symbolic is actually the real meat and the bone, let's say. Okay, so thank you for your attention. I'm happy to answer your questions.
Time for a question? Yeah.
So you use the simulator to try outcomes.
Yes.
Detect whether or not the action should be executed right now.
So if you have this simulation, you can do this and you can detect whether or not this action can be executed or not. But how can you have to develop a simulation up front for the situations you occur, or is this,
Yeah,
okay.
So I mean, so maybe I mentioned that we come out of this RoboCup context, and so what we are actually doing is we have some let's say objects, known object in this database. There can also be some unknown objects, and what we do is actually we back annotate. So the robot is actually something like taping a 3D representation of what's happening. Now, a fault is a sporadic instance. by taping this 3D thing, we can actually feed back this experience of that one fault has happened to this physical simulation. This physical is based on OpenRave using some physical simulator underneath, ODE or something, or Bullet. I think we use Bullet right now. And so by this, we actually enable machine learning. You see, the bad thing in faults is they happen once. And I mean, how can you, I mean, all these machine learning things, I mean, it's like hammering, yeah? So, I mean, after a while, you can be sure that the system is able to do what you want to do, but how can you make this happen if this happened once? That's the open issue, yeah? And what we did here, actually, so we back annotate the concrete experience of the robot. So how he went or she went there, picked up or identified this glass or not, or different objects, and put this kind of knowledge tree, or, well, this GEM, or let's say, yeah, we back annotate this to the physical simulator and use this for then, in this situation, trying to enhance the plan operator, which is not monotonic, maybe, yeah? So don't ask me about monotonicity. Yeah? I have no clue.
Thank you.
Okay, let's thank our speaker again.
Oh, sorry. Yeah, go ahead.
I can't translate. Can you help?
So let's see. I think we need to.
So the last talk will be about